Hello, let's discuss vertical curves. First, let me show you an example of plan and profile. So this is part of design of roadway. So in the plan, we design there the horizontal curves, which consist of spiral curve, simple curve, compound curve, and reverse curve. And all its elements should be recorded on a table. Well, on the other hand, on a profile, it is designed there the vertical curves. So because the profile, we are more concerned with the elevations of the stations of the proposed roadway. So let's take a closer look on the profile. So as you can see here, this red curve here is the existing ground surface. So that's the profile of the existing ground surface. And this blue curve here is the proposed roadway. So in designing a vertical curve, it shall consist again of tangents. So these tangents intersect at point of intersection. So right here in this design, we use PVI as the point of intersection, point of vertical intersection. So right here, this is a point of intersection, point of intersection. Now, depending on the design, we identify again the starting point and the end point, which is the PC and PT of the curve. So almost similar to the horizontal curve, we have PC and PT. So here, we can also use PVC to identify that this curve is a vertical curve, and that's the starting point of our vertical curve, PVC. And here's the endpoint, which is PVT. So these tangents have slopes. So it is given here, negative 2.11. It should be identified because it is also important that identifying the slope of the tangents shall not exceed to that prescribed maximum slope in making a roadway. So depending on the country, what is the maximum slope that should be followed in using and designing the profile or the alignment of, of the roadway. So let's start discussing what is a parabolic curve. So vertical curves are used to provide gradual change between two adjacent vertical grade lines. So the curve used to connect the two adjacent grades is parabola. So why parabola? Why do we use parabola as the curve for the vertical curve? Why not a circular curve with which is used on the horizontal curve? Why parabola? So when we recall the general equation of parabola, which is right here, x squared equals to negative 4ay, or this equals to y equals to negative x squared over 4a. When we take the first derivative of this equation, we have negative x over 2a, which is the first derivative, y prime, is the slope of the parabola. We take the second derivative of this slope, which means the second derivative of the slope, that's the rate of change of slope. So when we take the second derivative of the slope, we have negative 1 over 2a. So we don't have a variable here, which means that this value is constant. Therefore, the most preferable curve that we will use in designing a vertical curve is parabola, since the rate of change of slope is constant. So when we try to drive a roadway with an upward and downward slopes, so we experience the a constant rate of change of slope, or there will be no sudden upward motion when we drive on a roadway with vertical curves due to the design of the roadway, which is parabolic. So, what are the elements of a vertical curve? What are its parts? And what are the types of a vertical curve? So, we have symmetrical parabolic curve and an unsymmetrical parabolic curve. So, let's focus first on the symmetrical parabolic curve. Let's discuss all of these elements. Okay. Okay. So let's say this is the vertical parabolic curve or the symmetrical parabolic curve. So again, the starting point of this parabolic curve is PC, or the point of curvature. We can also use PVC, point of vertical curvature, and the end point is the PT, or we can also use PVT. So we have also the point of intersection where the two tangents intersect, which is PI or PVI. Then the length of parabolic curve is measured horizontally. Okay, this is measured horizontally, not the length along the curvature. So in symmetrical or in vertical curves, we measure here the horizontal distance of the curve. So that's what matters in determining the length of parabolic curve. Let's say L. So of course, in a symmetrical parabolic curve, it means that the tangents from PC to PI and PI to PT has the same length, which means this distance are the same. Okay, so if this is the total distance of curve, just take the half of it. That's the distance. This is symmetrical parabolic curve. Okay. By the way, this curve, which is going upward at PC and goes down uh, towards PT, uh, this type of curve is a summit curve. On the other hand, if we start at a slope or a tangent which is downward and upward tangent, which having a curve like this will be a sag curve. Okay, so let's go back here. Again, the tangent from PC to PI is also called as back tangent, while the tangent from PI to PT is the forward tangent. Okay, again, this is a summit curve, which means that in a summit curve, there will be a point which is the highest point on the curve. So let's say this is the highest point on the curve, HP. So that will be the highest point. So how do we determine the highest point on a summit curve? So we can use a formula by identifying the difference in elevation from PC to the highest point, and that is H1, while the horizontal distance from that, from PC to the highest point, is S1. So later we will discuss the solutions on these values, S1, H1. Now if our reference point is from PT, so the distance from PT to the highest point is S2, while the difference in elevation from PT to the highest point, that's S2. So the back tangent and forward tangent have given grades, G1 and G2. So upward is positive, downward negative, from left to right. Okay. So we also have here h, which is the vertical distance between pi and the curve. This one right here. This is h. Okay, that's h. Now, if it is required there that we need to identify the elevations and stationing at any point on the curve, let's say we're required to determine the elevation and stationing at this point. So we will be required to determine y here and the horizontal distance x. Okay, so y and x, there will be corresponding solutions in determining these values. Okay, now let's use a grade diagram. As I've said earlier, the rate of change of slope of the parabola is constant. So initially, we have a maximum slope at PC, which is the slope of G1. So as we continue the stationing from PC going to PT, so the slope at each point tangent to that point gradually changes constantly, where when we reach the highest point on the curve, we will have a zero slope tangent at that point. Therefore, here on this grade diagram, the location of the grade or the location of the highest point when we make a grade diagram. So we have G1 here, we have G2 here. So in the grade diagram, the location of the highest point is the point in which the slope is zero. So this is zero, this is zero. So this is positive, this is negative. So this grade diagram here, this is used in deriving the formulas in determining the S1, S1, H1, and that is necessary in also determining the elevation and stationing at any point. So I will have a separate video on how the formulas are derived. So here in this video, I will just present you the formulas used in a symmetrical parabolic curve. So let's proceed. So let's discuss now the formulas that we will use. So one fundamental formula that we can use here is the slope is equals to rise over run, okay, or the vertical distance over divided by its horizontal distance. So that's it. So here are the derived formulas. We have A and B. A and B is just the difference in elevation from PC to the point of intersection. That's A. So that's necessary if we are required to determine the elevation at PI, or if the given elevation is at PI and we want to determine the elevation at PC. A is uh, is useful in determining that elevation. The same way as B, the difference in elevation from PI to PT. S1. S1 is the distance from PC going to the highest point or the lowest point of the parabolic curve. So this would be the formula G1 times L over G1 plus G2. So here in this formula, we take the absolute value of G1 and G2. So let's use all positive signs because we have an upward slope, positive, downward slope, negative. So take the absolute values of these. Same way as this S2, the distance from the highest point or lowest point to the point of tangency. We have H1. H1, as you can see here, H1 and H2 is the difference elevation from PC to highest point or the lowest point. h2 from PT going to the highest point. So that's it. Um, as you can see, h1 and h2 is just derived from the area of this triangle on the grid diagram. When we take the area of this, that's 1 half G1S1. Area of this one, 1 half G2S2. So that's H1 and H2. For H, we have L over 8 times G1 plus G2. So in determining the H, also take the absolute value of G1 and G2. So this one, from PI to the curve, that's H. So also if we draw a chord, let's say chord from PC to PT, or a line from PC to PT, so the vertical distance from that line to the curve is also H. Okay, another useful formula is we take the squared property of parabola. Eh, Using this, uh, we can compute the value of y, parabola. We can compute the value of y, but it's required there to have the value of h, and then so we take uh, the ratio of the square of x over y is equals to half of the vertical curve L over 2, take the square of it divided by the vertical distance from PI to the curve, which is h. Okay, so these are the formulas that we will use in this problem. So let's now start answering some sample problems. A grade line AB having a slope of positive 5% intersects another grade line BC having a slope of negative 3% at B. Determine the elevation and stationing of the summit of the 120-meter parabolic vertical curve to connect the grade lines. A is at PC with a stationing of 5 plus 200 meters and an elevation of 100 meters. So let's draw the figure. Okay, so here's the figure. We have a slope of positive 5% for the back tangent, and forward tangent with a slope of negative 3%. So assign that as G1 and G2. So we will determine the highest point on the curve. So we don't know yet if the highest point is right here or on this side. So we will be able to determine that using the formulas. So the summit of a 120-meter parabolic vertical curve. So it means from PC to PT, that's 120 meters. And from PC to PI, we have 60 meters. And PI to PT, that's also 60 meters. So the stationing is 5 plus 200 and elevation is 100 at PC. Okay. So the solution here, we determine first if we want, since we have the stationing given at PC and elevation at PC, we determine the stationing first by computing S1, or the distance from the PC to the highest point. So S1 has a formula of G1 over L plus G1 plus G2. So just ignore the sign for the slope or for the grade of each tangent. So that's 0.05 and 0.03. So just take the absolute values so that we have a positive value of 75 meters when we compute the S1. So 75 meters means from point A, so it is approximately located right here. the highest point. So this is your S1 from the highest point to PC. So from that, we can now determine the stationing of the highest point. The stationing of highest point, so we will just use here the horizontal distances. Okay, we need not to use the distance along the curve. We need only the horizontal distance S1. So stationing at PC, we will just add S1. So stationing of highest point is equals to station 5 plus 200 be added by S1, which is 75 meters. So the stationing at the highest point is equals to station 5 plus 275 meters. That's it. That's your stationing. Okay. Next, for the elevation, since we already have the the location of the highest point, the horizontal distance, so the elevation of the highest point is computed by determining the difference in elevation from PC going to the highest point. So you use blue. Here, this vertical distance here. So that's H1. So the H1 here is computed by the formula 1 half G1 S1. Okay, so 1 half G1 is positive 5%, S1 is 75. Okay, so H1 is, when we compute this, 1.875 meters. So the elevation of the highest point is just elevation of the PC added by H1. So we can now compute the elevation of the highest point by adding the elevation at PC, which is this one, 100 meters, plus H1, which is 1.875 meters. Okay, the elevation of the highest point therefore is 101.875 meters. That's your answers for this problem. Okay, this one and the one. The next problem. A grade of negative 4% intersects a grade of 3% at station 11 plus 488 of elevations 20.8 meters, which means that point is the point of intersection. These two center grade lines are to be connected by a 260-meter vertical parabolic curve. At what station is the cross drainage pipes B situated? B. If the overall outside dimensions of the RC pipe to be installed is 95 centimeters and the top of the culvert is 30 centimeters below the subgrade, what will be the invert elevation at the center? Okay, so let's draw the figure. Okay, so in the problem, it is not mentioned there that the parabolic curve is unsymmetrical. So we can easily assume that this parabolic curve is a symmetrical vertical curve. So given there are the grade, which is negative 4%, which is the back tangent, and forward tangent of positive 3%, which means that we will form a sag curve here. Okay, this is a sag curve. So the opposite of summit curve. So these two center grade lines are to be connected by a 260-meter parabolic curve. So the total distance from the starting point to the end point is 260 meters. So assuming that it is a symmetrical parabolic curve, we divide it equally from PI going to PC and PT, which is 130 meters each. So at what station is the cross drainage pipes be situated? Okay, so uh, in locating the best location for the cross drainage pipe, the best location for that is the lowest point on the subcurve, because that's the location where the water will go, which is the lowest point along the curve. So that's the best location for the drainage. That's why we are required here to determine the lowest point on the curve. So we assume that it is right here, but we can prove that it is right here, the lowest point, because we can compute that using the formula. Okay, so let's use the formula. So given here the stationing and elevation at point of intersection. Okay, so let's compute first the stationing of the of lowest point. So the stationing of lowest point, we can have a reference point from PC. So stationing of lowest point is equals to the stationing at PC, and just add S1. On the other hand, we can use PT as the reference point in determining the stationing of the lowest point. But we have to subtract S2 because we're going backward. So that's S2. This is S1. Okay. So you can use either this one or that one. So let's say we use the second solution, where we use PT as the reference point, okay, in determining the lowest point. So the formula is, we determine first S2. S2 is equals to G2 L over G1 plus G2. So take the absolute value of the grades. You have 260 over 0.3, 03, and so this is 0.03, 0.03, and 0.04. Okay, this is S2. S2 therefore is 111.429 meters. Next, so we have a given stationing of the point of intersection. So to determine the stationing of PT, which is right here, we will add the horizontal distance from PI to PT, which is half of the length of cell curve, which is 130 meters. So let's determine first the stationing of PT. Stationing of PT is equals to stationing of PI, okay, here, which is station 11488 plus L over 2. Okay. Stationing of PI is station 11 plus 488 plus 130 meters. So stationing of PT is equals to station 11 plus 618 meters. So it's stationing of PT. We have stationing of PT, then subtract this distance S2 to determine the location of the lowest point. Okay, stationing of lowest point is equals to stationing of stationing of PT minus S2. So station of PT, station 11 plus 618 subtracted by 111.429. Okay. Stationing of the lowest point. Subtract that. We have station 11 plus 506.571 meters. Okay, that's your stationing at the lowest point. Okay. Which is that's for letter A. Letter B, the overall dimension, outside dimension of the reinforced concrete pipe to be installed is 95 centimeters, and the culvert is 30 centimeters below the subgrade. What will be the invert elevation at the center? Okay, so let's say this is the lowest point. So we put the drainage here or the culvert here embedded at a depth of 30 centimeters below the subgrade or below the roadway, and we have an outside dimension of 95 centimeters. So what will be the invert elevation? So let's draw. So the equivalent drawing for that is right here. Okay. So in the sample problem, it is not given there the thickness of the culvert, but uh, in reality, the invert elevation is this one, the lowest point on the inside, on the inside of the culvert. Okay, or if we have a canal, okay, line canal, the invert elevation is right here, the lowest point on the surface or the inside surface of the drainage structure. So since we have the thickness of the culvert is not given, so we can assume that the the thickness is almost negligible. That's why the invert elevation is just the lowest point on the culvert. So, but if the thickness of the culvert is given, what the invert elevation is right here, because that's the lowest point where the water will go when the water will travel at this point. Okay, so let's determine the elevation at this point, the invert elevation of the culvert. So of course this is the lowest point. So what we need to do is determine the elevation at lowest point and subtract. Okay, subtract the depth 0.3 and the outside diameter of 0.95. Okay, so let's solve. First, we need to determine the elevation of lowest point. Okay, determine the elevation of lowest point. This is for letter B, elevation of lowest point. So how to determine the elevation of lowest point? Okay, since earlier we used PT as the reference point, okay, going to the lowest point here, we use that again, and we determine H2, which is the difference in elevation between the PT and the lowest point. So the elevation of the lowest point with the reference from PT, we subtract that H2. So H2 is equals to 1 half G1, G2, sorry, G2 is 2. So H2 is 1 half G2, 0.03, and S2 is 111.429. So earlier. So H2 is 1.671 meters. Okay, the elevation of the lowest point is equals to elevation of PT. We don't know yet the elevation of PT minus H2. So how to determine the elevation of PT? Okay, so we need to determine this vertical distance. So the formula that we can use is for letter B, or we can just use the concept of slope is equals to rise over run. So the rise here is the vertical distance, run is the horizontal distance between 2 points, and we have the slope, which is the grade. So if we want to determine this rise here, so we just multiply the run by the slope. That will be rise. Okay. So to determine this vertical distance, which is B, just multiply the slope, which is G2, by the run, which is the horizontal distance, 130 meters. Okay. So that is 130 meters. So B is equals to 0.03 times 130 meters. We can now determine the elevation at PT equals to elevation at PI, and we add this vertical distance B. Okay, from PI, add the vertical distance, which is 0.03 times 130 meters is equals to 3.9 meters. So elevation of PI added by P. So elevation at PT is equals to elevation of PI, which is 20.8. It's 20.8 here, 20.8. Just add B. I can now determine the elevation at PT. So elevation at PT is equals to 24.7. 24.7 meters. Substitute that elevation at PT right here. So elevation of PT is equals to 24.7 minus H2, which is 1.671 meters. So the elevation, therefore, of lowest point, when we subtract the two, we will have an answer of 23.029 meters. So elevation of lowest point is 23.029 meters. That will be used in determining the invert elevation. Okay, so let's substitute now the elevation at the lowest point, which is 23.029. Okay, okay, good. So solution for the invert elevation, i.e., is equals to 23.029. Just subtract this vertical distance, 0.3 and 0.55. So subtract the 3, we have an invert elevation of 21.779 meters. That's your final answer. Okay, so you can use as alternative solution when you take the reference point of PC when locating the lowest point. So you try also solving it using PC plus S1 to locate the stationing of the lowest point, and you can also determine the elevation of it using PC again minus H1. So you can use also that alternative solution and you will arrive also with the same answer. Okay, so let's discuss the unsymmetrical parabolic curve. An unsymmetrical parabolic curve is a vertical curve using two or more parabolic curves placed adjacent to each other. So it means that we have here two symmetrical parabolic curves placed adjacent to each other. So this one is the first curve, which is a symmetrical parabolic curve, and the second curve, vertical curve, is this one. Okay, so we have two solutions that we can use in solving problems in unsymmetrical parabolic curve. The first one is formula based, and the second one is we solve the common tangent G3. Okay, so it means that if this is the point of compound vertical curve, or the point where the two curves meet, so it means the tangent at that point are the same on the first curve and the second curve. So when we compute the grade of that tangent, now we can solve the first curve, the vertical parabolic curve, and the second curve separately, depending on the required. So we can now solve this symmetrical parabolic curve and this symmetrical parabolic curve also using the principles and solutions and formulas in a symmetrical parabolic curve. Okay. So let's now solve some example problems in an unsymmetrical parabolic curve. First, let me discuss to you the formula when we solve the problem using the formula-based one. So we have h here. H is the distance from Pi to the point of compound curvature, or the point of compound curve, or the point where the two curves meet. Next, we have L1 and L2 times G1 plus G2 over 2, the quantity of L1. So L1 and L2 are the length of each curve. Okay, L1, this is L2, and G1 and G2 is the tangent of the first curve, or the back tangent, and the forward tangent of the second curve is G2, the grade. So if G1 L1 over 2, or the absolute of G1 L1 over 2, is less than the computed H, uh, we use the formula for S1, which is equals to G1 L1 squared over 2H. But if G1 L1 over 2 is greater than H, we use this solution S2 G2 L2 squared over 2H, which means a reference point here in computing the lowest point or the highest point of an unsymmetrical parabolic curve is from PC. This one is from P. So we use again squared property of parabola if the required point is required for the elevation stationing of a required point, which is at any point on the curve, uh, depending again on the absolute value of J1 L1 over 2. If it is less than H, we use this squared property of parabola, x squared over y equals to L1 squared over H. And if G1 L1 over 2, the absolute value of it is greater than H, we use this solution, x squared over y equals to L2 squared over H. Now, so if we will not use the formula-based solution in computing the elevation and stationing of any point on a symmetrical parabolic curve, we use this alternative solution, which is we compute the grade of the common tangent, G3. Okay, so here, unlike the solution here where we neglect or we take the absolute value of the grades or the slope of each tangent, here in G3, we use the positive and negative sign of the corresponding tangents. So we have G1 L1 plus G2 L2 over L1 plus L2. So let's now solve sample problem number 1. An unsymmetrical parabolic curve has a forward tangent of -8% and a backward tangent of positive 4%. The length of curve on the left side of the curve is 40 meters long, while that of the right side is 60 meters long. The PC is at station 6 plus 800 and the elevation of 100 meters. Compute the stationing and the elevation of the highest point of the curve. So let's draw. Okay, so here's the figure. We have 40-meter length from PC to PI, and L2 is 60 meters on the right side, 60 meters long from PI to PT. Stationing of PC 6 plus 800, elevation 100 meters. Compute the highest point of the curve. So our assumption is the highest point is right here, but we can verify that by computing the location of the highest point. So the first solution is we use the formula-based solution, in which uh, we compute first h. So as we recall the formula, we have h, which is equals to L1, L2, G1 plus G2 over 2 times L1 plus L2. So L1 is what? 40 meters. 40, L2 60, G1 4%, 0.04, and G2 is 8%. So take the absolute value of that, positive. Okay, 2 times L1 plus L2, 40 plus 60. So the computed H is, when we compute this, we will have an answer of 1.44 meters. Then take the absolute value of G1, L1 over 2. So we compare the answer of this to H. So 0.04 times 40 over 2. The answer is 0.8. So it means that G1 L1 over 2, which is 0.8, is less than the computed H. Therefore, we can use the solution for the location of the highest point. S1 is equals to G1 L1 squared over 2H. So substitute that 0.04 times 40 squared over 2 times 1.44. So the S1 is 222.222 meters. Okay. So we can now locate the stationing stationing of the lowest point, of the highest point rather. HP is stationing of PC plus S1. So stationing of 6 plus 800 plus 22.222. Okay. Stationing of the highest point is equals to station 6 plus 822.222 meters. That's the answer here. But we are required to determine the elevation, right, of the highest point. So the next solution, since we already have the S1, so S1 is the distance from PC to the highest point. So that's 22.222, which is less than 40. So it is on the left side of the curve, which means it's right here. So elevation of the highest point is, what we can do here is we determine first the difference in elevation at this point. Okay. So given the slope of G1 and the horizontal distance, we can determine this total vertical distance. which is, recalling again, the slope is rise over run. We can determine rise by multiplying the slope, which is g1, by the run, or the horizontal distance, s1. So we can determine this vertical distance here. So computing that, we have g1 of 0.04 times s1, which is 22.22. We have a total vertical distance here of what? 0.889. 889. So that's your vertical distance here. Okay. Then the other value that we need to compute here is this distance y. So this distance y here, when we compute y, we will use the squared property of parabola. So according to the formula, if the g1 L1 over 2 is less than h, okay, we will use x squared over y equals to L1 squared over h. So comparing again, g1 L1 over 2.8 less than h. So going back to the formula it showed earlier, this solution is applicable in determining y. So let's determine y, because if we are going to determine this, the elevation at this point, the elevation of the highest point shall be computed by the given elevation at PC, then add this vertical distance here so that we can determine the elevation at this point, okay, which is 0.889. Then we will subtract this y value here, which is the distance from the tangent to the curve at any point. So the chosen point is the highest point. So we need to determine this y here. So let's uh, determine y. So let's isolate y. In this given equation, we will have h x squared over L1 squared equals to y. So that's the solution determining the y. So y therefore is equals to h. The computed h is what? 1.44. So h is 1.44 x squared. So x is 22. So our x here is also this one. So the chosen point or the location that we need to determine. So the horizontal distance from the PC to that point is x. 22.22. But last, if the point is nearer at PT, your x there should be measured from the PT. Okay, but here it is located near PC, so our x is right here. Okay, take the square of this, and L1 is 40 square. So computing this, we have 0.444 meters. Okay, so that's the y. We can now solve the elevation of the highest point. Elevation of the highest point is equals to elevation of PC, which is 100 plus 0.889 minus 0.444. The elevation at the highest point therefore is equals to 100.445. Okay, so that's the final answer on the elevation of the highest point. Okay, that's solution number 1. For solution number 2 class is to determine the grade of the common tangent. Solution number 2, G3. Uh, Solution number 2, G1 L1 plus G2 L2 over L1 plus L2. So here we use the signs of G1 and G2 to identify the sign also of the slope of G3. So substitute all the values of G1 and G2. Back G1 is positive 4%, G2 is negative 8%, L1 40, L2 60. Okay, so 0.04 plus 4%, 40 plus negative 0.08, and 60 over 40 plus 60. G3 is equals to, when we compute this, we will have an answer of negative 0.032, or in percent, we have a negative 3.2%. So that's the grade of the common tangent. Okay, grade of the common tangent. So this is the figure. So if you have a negative G3, so it means it is going downward from left to right. So this is G3 here, negative 3.2%. Negative 3.2%. So after that, when we have the common tangent, we take both sides as separate symmetrical parabolic curve. Then we compare their grades. So usually, uh, the side which has the positive and negative grades, that's the location of the highest point. As well as on a subcurve, the one with the negative and positive grade, that's the location of the lowest point. Because right here, if on the right side all grades are negative, which means this side has the lower elevations because both tangents are going down. But right here we have an upward tangent and downward tangent, so which means somewhere here is the location of the highest point. Okay, so we choose the left side of the unsymmetrical parabolic curve, and we focus on that side and solve it using the solutions on a symmetrical parabolic curve. So, so this is the PC. We solve now the highest point by determining H1 and S1. So the S1 on a symmetrical parabolic curve is G1 L over G1 plus G2. But right here, the second tangent or the forward tangent here is G3. So G1 plus G3. Okay, all positive for the grades. We will have 0.04 times 40 over 0.04 plus 0.032. Okay, solving that, we have an S1 of 22.222 meters, which is the same on the formula-based solution for the S1. So for the stationing of HP, we have stationing of 6 plus 800. Okay, station 6 plus 822 or 222 meters. Okay, so same answer here on the formula base. Next, the elevation of HP. Highest point, the elevation of PC plus H1. Okay, so H1 is equals to uh, 1 half G1 S1. So we already have S1, uh, 1 half G1 G1 is 0.40464%, and S1 is 22.222. Okay, so the H1 is 0.444 when we compute. So elevation of HP is equals to elevation of PC, which is 100 meters, plus H1, 0.444 meters. So elevation of the highest point is equals to 100.444. That's your answer. Okay, so right here we have 100.445 because due to rounding off, I think, of some values here during the computation, there's a slight difference on the decimal place of the final answer on the highest point elevation. Okay, so the two solutions have identical, almost identical answers. But I think the most reliable solution is this second solution where we compute the grade of the common tangent. Okay, and just take them as separate symmetrical parabolic curve. Okay, so let's proceed to the last example. Negative 4% grade meets a positive 6% grade near an underpass. To maintain the minimum clearance allowed under the bridge and at the same time introduce a vertical transition curve, and the grade lies 200 meters on one side of the vertex of the straight rod and 100 meters on the other. The station of the beginning of the curve, 200 meters side, is 10 plus 000, and its elevation is 220 meters. Determine the stationing and elevation of the lowest point of the curve. So let's solve this. Okay, so here's the figure. We have G1 negative 4% meets a positive 6% grade at an underpass. So we have L1 of 200 meters on the left side because the station the beginning of the curve is 200 meters side, and we have L2 100 meter on the right side. Okay, then the given stationing is 10 plus 000 and elevation of 220 meters at PC. Determine the stationing and elevation of the lowest point of the curve. So here we assume that the lowest point is right here on this subcurve, but we can still verify that by computing the S1 or S2 of this unsymmetrical curve. So let's say in this problem we use the formula-based solution in computing in determining the lowest point station and elevation. So in determining the stationing first, so the stationing of the lowest point, if it is nearer in PC, we just add S1. On the other hand, if the lowest point is near at PT, we use PT as the reference point and subtract S2, which is right here. So we must verify what solution we will use in this problem by computing first the H. H is L1, L2, G1 plus G2 over 2 times L1 plus L2. So the H is equals to 200 times 100 times 4% plus 6% over 2 times 200 plus 100. So H is equals to, computing that, we have 3.333 meters. Oh, Next, we have to compare that h to G1 L1 over 2 or G2 L2 over 2. Compare first to G1 L1 over 2, which is equals to 0.04 times 200 over 2 is equals to 4. So it means that G1 L1 over 2 is greater than h, which means the solution that we will use here is S2 G2 L2 squared over 2h. Okay, this is the solution that we will use in determining the location of the lowest point, which means the lowest point is nearer at PT. Okay, so our assumption is correct. So S2, we can now solve S2 by substituting G1 that's G2 0.06 times L2 100 squared all over 2 times h. Computed h is 3.333. Okay, so S2 is equals to 90.009 meters. So this is 90.009 meters. Okay, the stationing of the lowest point therefore should be stationing of PT minus S2. So first determining the station of PT should be stationing of PC plus L1 and L2 since the given stationing is at PC. So we must add L1 and L2 to locate this stationing. So L1 plus L2. So station PT is equals to station 10 plus 000 plus uh, 200 plus 100. Okay, so we have station 10 plus 300 for the stationing of PT. Can allocate the stationing of the lowest point by substituting stationing of PT and subtracting S2, which is 90.009. So the stationing of the lowest point is equals to station 10 plus 209.991 meters. That's your answer on the stationing of the lowest point. For the elevation of the lowest point, okay, going back here, we don't have yet the elevation of PT. So let's determine first the elevation of PT before we proceed on determining the elevation at this point, okay, at the highest point, lowest point. Okay, so the elevation of PT should be, we determine this vertical distance, let's say A, we subtract that so that we determine the elevation of PI. Then we add the difference in elevation of PI and PT, let's say P, in order to determine the elevation of P. So therefore, elevation of PC minus A plus P. So this vertical distance here can be determined just multiplying the grade of the tangent to the equivalent horizontal distance. So A is just 4%, okay, negative 4%. So negative 4% times 200 plus, because this is positive, 6% of 100. Okay, let me rewrite that. We have 220. Yes, we have 220 meter minus 0.04 times 200 and we have positive 0.06 times 100. Okay, we have now the elevation at PT. Elevation at uh, PT is equals to 218 meters. So this is 218 meters. So now, how do we determine the elevation of the lowest point given the elevation at PT? So the elevation of the lowest point is equals to the given elevation at PT. Then, uh, when we compute the distance from the tangent to this point, that's y. So what we need is to determine the elevation at this point by simply computing the difference in elevation at this point from the PT. So that vertical distance is just the product of this grade G2 and S2. So all we need to do is subtract that vertical distance here, which is G to S2, and just add Y. Okay, so let's now compute. Let's compute Y. Y can be solved by using again the squared property of parabola. So right here, uh, G1 L1 over 2 is greater than H. Therefore, we use x squared over y equals to L2 squared over H. So determining y, we can rewrite the equation into x squared H over L2 squared. Okay, substitute. Our x here is from PT to lowest point, the horizontal distance, which is S2. That's your x. So we have here S2 of 90.009 squared times the h. Computed h is 3.333 over L2 squared. L2 is 100. Okay, so y is 2.7. Y is 2.7 meters. We can now compute elevation at the lowest point. The elevation at PT is 218 meters minus G2 is 6%. That's 0.06 times S2. Okay, S2 is 90.009. Then add Y, 2.7. Okay, let's compute. So the answer here is 215.299 meters. That's the elevation of the lowest point. Okay, that's your final answer. Plus, my homework is for you to solve this using the second solution by computing the grade of the common tangent and verify that you have similar answer on the lowest point, station, and elevation. Okay, thank you. That ends my lecture on vertical curves. God bless.